The last thing that we're going to look at in this section is the binomial series. Now the binomial series is also listed right here. Let's learn how to use it so that we can find our series. The binomial series says that if you have a function and that function is 1 plus x raised to the k power where k doesn't equal 0, then the binomial series is this expansion. It's 1 plus k times x plus k times k minus 1 times x squared all over 2 factorial plus k times k minus 1 times k minus 2 times x cubed all over 3 factorial plus all the way down to the nth one, which is k times k minus 1 times k minus 2 times k minus n plus 1 times x to the n all over n factorial. So we're going to use the binomial series to find the Maclaurin series. The Maclaurin series means we are centered at 0 for the following functions. So I have f of x is equal to 1 divided by 1 minus x raised to the 4th power. The first thing I need to do is I need to get it to look like this. That's not in the denominator, and it also has a plus sign, so I need to rewrite this guy. Well, I know that in order to get it out of the denominator, I have to make this exponent negative, so I could rewrite this as 1 minus x raised to the negative 4th power. I also need this guy to be a plus sign. It's not a plus, but I know that I could make it a plus by saying 1 plus negative x, and again all of this raised to the negative 4th power. Now I can determine what is my x and what is my k. My x in this problem is going to be negative x. And my k in this problem is going to be negative 4. So I'm going to use these two pieces of information to create my binomial series. So I know that 1 over 1 minus x raised to the 4th power is going to equal 1. And you can always think of this times x to the 0 over 0 factorial. I always put those in because I think it helps. So remember, what is x here? My x is negative x. So negative x to the 0 all over 0 factorial plus k. Well, k, remember, is this guy, negative 4. And then x, which is negative x in this case. And that's raised to the first all over 1 factorial. I didn't write it in, but you know that at this point those always happen. Plus the next one is k times k minus 1. So k again is negative 4. Negative 4 minus 1 is negative 5. And then it's x, which is negative x. I square it and I put it over 2 factorial. Plus, and I usually go down about to the 4th power if I can. So it's going to be k times k minus 1 times k minus 2 times x, which is negative x, cubed all over 3 factorial, one more, and then it's k times k minus 1 times k minus 2 times k minus 3 times x raised to the 4th power all over 4 factorial, and then plus dot dot dot. So what I want to do now is to come up with a power series for this particular example. Remember, this is always when n is equal to 0, when n is equal to 1, when n is equal to 2, n equal 3, n equal 4. What do I notice? Well, I notice right away that this is an n factorial in that denominator. So I'm going to go ahead and just do n factorial in the denominator. Then, because your x here was negative, let's actually figure out if we're positive or negative first, and then deal with the x. So this is really a positive, because this is going to be 1, and then that's going to be negative to the 0, so that's just going to be really a positive number. Here I have a negative times a negative 1 raised to the first, so that ends up being a positive number. Here I have a negative times a negative, which is a positive. A negative squared, all of that makes a positive number. Here this is a negative times a negative times a negative, which is negative. But a negative cubed is negative, so all of this multiplied together makes a positive number. Here, negative, 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 negative to the 4th. So 4 negatives multiplied together is positive, and negative to the 4th is positive. So I have a positive number. I don't alternate for this particular series, so I won't need a negative 1 to the n. Now that we've dealt with the positives and negatives, so that alternating piece, if I were to rewrite what we have here, and I'm going to write it underneath, so closer to where I have our numbers that we're plugging in here. This is just a 1 and then an x to the 0, and this is a 4 and an x to the first, and a 4 times 5, and an x squared, and a 4 times 5 times 6, and an x cubed, 4 times 5 times 6 times 7, and an x to the fourth. Now that I got rid of the negatives, this is really what's left. A 1 times an x to the 0, a 4 times an x to the first, a 4 times 5 times an x squared, a 4 times 5 times 6 times an x cubed, a 4 times 5 times 6 times 7 times an x to the fourth. Hopefully you notice now, when n is equal to 0, I have x to the 0, n equal 1, x to the 1, n equal 2, x squared, etc. So we're really used to that by now. We know that that's just x to the n. But what else is happening? Look at these numbers that I have. They look kind of like a factorial, right? Looks like I'm multiplying 7 times 6 times 5 times 4, but I'm missing something from here. I'm not getting all the way to the end for the factorial. I'm missing a 3 times 2 times 1, right? I'm missing those three numbers. Same thing here. This looks like a factorial, 6 times 5 times 4, but I'm missing a 3 times 2 times 1 to end that factorial. Same thing here. I'm missing a 3 times 2 times 1, and here I'm missing a 3 times 2 times 1. Now, if you're missing a 3 times 2 times 1, you're missing a 3 factorial. So this denominator looks like it might be a 3 factorial. But what about the top? Well, look here. When n is 4, you're at 7, and then you're multiplying 7 down. Well, isn't that just an n plus 3 factorial? And here, when you're at 3, you're multiplying 6 down. Yeah, that looks like an n plus 3 factorial. Here at 2, you're multiplying 5 down, n plus 3 factorial. Here at 1, you're multiplying 4 down, n plus 3 factorial. Here at 0, well, it doesn't have a number, but if you think about it, if you had an n plus 3 factorial and you were plugging in 0, that's 3 factorial, which is a 3 times 2 times 1. But if you're missing a 3 times 2 times 1, wouldn't that just be 1? Yeah, exactly. So the numerator here is n plus 3 factorial, and then your denominator is 3 factorial. So the series for 1 over 1 minus x to the fourth is the sum from n equals 0 to infinity of n plus 3 factorial times x to the n, all over 3 factorial times n factorial. Let's look at example 9. Example 9 is f of x equals 1 over 2 plus x cubed. Recall, the binomial series was f of x equals 1 plus x to the k. So first, I don't have a 1. I have a 2, so that's a problem. It's not in the numerator, it's in the denominator. That's a second problem. The only thing I have that I didn't have last time was the plus sign, so I have at least something. But I need that to be a 1. Well, how would I make that guy a 1? Well, I'd have to factor out a 2. So think of it this way. If I factor out a 2 from this guy, I'd be left with 1 plus x over 2. Because if I factor out a 2 from 2, I'd be left with 1. If I factor out a 2 from x, I'd be left with x over 2. Notice that I put that whole thing with cubed on the outside because I'm factoring it from the inside of that parentheses. If I distribute the third power here, what is 2 cubed? Well, 2 cubed is 8. So this is really 1 over 8 times 1 plus x over 2 cubed. Now let's write this without the denominator, so make that exponent negative, and that becomes 1/8 times 1 plus x over 2 to the negative third. Now I'm in a great format to find that binomial series. This 1/8 here is just a constant multiplier, so it's just going to multiply along. My x is going to be x over 2, and my k is going to be negative 3. So we know that 1 over 2 plus x cubed is going to equal, don't forget about your constant multiplier, 1/8. And then let's build it out. So I'm going to open a bracket so we can start listing out those numbers. Remember, it's always going to be 1, and then that's going to be times x to the 0 over 0 factorial, and then it's plus k in this case is negative 3 times x, which is x over 2 to the first, all over 1 factorial plus k, which is negative 3, k minus 1, negative 4, x, which is x over 2, squared, all over 2 factorial plus, and then we have k minus 1, k minus 2 times x raised to the third power all over 3 factorial plus, last one that I'll put in here, it's k minus 1, k minus 2, k minus 3 times x raised to the fourth all over 4 factorial and then plus dot dot dot. And all of these things that I'm saying are coming from that formula. This guy here, 1 and then k times x, k times k minus 1 times x squared all over 2 factorial, k times k minus 1, k minus 2, x cubed all over 3 factorial. So it's coming from that formula there. And remember, the x in this case was x over 2, which is why I keep writing x over 2. And then the k there was, what, negative 3? So that's why it's negative 3, and then negative 3 minus 1 is negative 4, and then minus 2 is a negative 5, minus 3 is a negative 6, etc. Just like last time, we have to figure out what this formula is. So what is the formula that matches this? Well, I notice that I have that n factorial again, right? 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So I notice I have that n factorial. What else do I notice? Well, I notice that I am positive here, but here I am negative, and then 2 negatives make a positive, and then 3 negatives here will make a negative, and then 4 negatives here give me, that ends up being positive. So I notice that I'm alternating between positive and negative terms. Since I'm alternating between positive and negative terms, I know that I write a negative 1 to the n. Now what else do I notice? Well, let's write the things down underneath it just so it's easier to see. Well, here I'm left with a 1 and then an x over 2 to the 0, here a 3, and an x over 2 to the first, here a 3 times 4, and then an x over 2 squared, 3 times 4 times 5, and then an x over 2 cubed, and then finally 3 times 4 times 5 times 6, and an x over 2 to the fourth. First thing I notice is that I have an x over 2 raised to the n. Because remember, this is when n is equal to 0, when n is equal to 1, when n is equal to 2, when n is equal to 3, when n is equal to 4. So I definitely have an x over 2 to the n. So I'm done with these. I don't need to worry about them anymore. Now I'm just looking at those numbers. Well, notice that it looks like a factorial again. What am I never multiplying by? Well, I'm never multiplying by 2 times 1, right? Those are the things that I'm missing. Since it's the one that I'm missing, remember that's what goes in the denominator, and that's just a 2 factorial. What is the other thing? Well, when I'm 4, I'm at 6. So isn't that an n plus 2 factorial? And when I'm at 3, I'm at 5. That's an n plus 2 factorial. When I'm at 2, I'm at 4. Again, n plus 2 factorial. So it looks like I have an n plus 2 factorial in the numerator. So this series, 1 over 2 plus x cubed, is actually 1/8 times the sum from n equals 0 to infinity of negative 1 to the n times n plus 2 factorial times x over 2 to the n all over 2 factorial times n factorial. Now you can leave it like that, but you'll notice that WebAssign or the textbook will clean it up. Again, you can leave this. This is perfectly fine. You don't have to clean this up. But what WebAssign will do is it's going to rewrite this as x to the n, and then in the denominator 2 to the n, and 2 factorial is just going to be 2. And then they're going to say, hey, my bases are the same, so what I need to do is I need to add those exponents. Oops, I forgot my factorial there. And that becomes 2 to the n plus 1 times n factorial. So you can clean it up if you want to, or you can enter it in just as we had here. This is perfectly acceptable on a test or in WebAssign.